So the next one is the Faraday's law. The Faraday's law. Faraday's law is easier than the Ampere's law a bit. So I try to present it first. For the Faraday's law, you know that the time varying, if you have a time varying magnetic flux, then you will induce a induce EMF. So it can be written as a line integral of the electric field. So according to the Stokes law, the left-hand side, we can rewrite it as a double integral over the area, And the stuff we need to do is take the curl of the electric field. So we substitute this one into here. Then we will get this term equals to this term. And we put the time derivative into the integral so that we write it as a partial derivative with respect to time. And with a similar agreement, because the loop is arbitrary, so that every point should be the same to make the whole integral to be agreed with each other. So that this one should equals to this one with the negative sign. So we can write the differential form of the Faraday's law like this. The curl E equals to minus partial B partial T. So this is how we derive the differential form of the Faraday's law. Any questions? So next is the Ampere's law. It's a bit more complicated, but well, it's fine. So for the Ampere's law is something like if you have a current going through an area, and also the time varying electric flux going through the same area, then it will induce a magnetic field on the boundary of this area. And using the Stokes law on the left-hand side, we can write it as curl B and take the double integral over that area. And we substitute this part into the left-hand side, so we will have something like this, and then we put mu0 into the integral, and we also put epsilon 0 ddt into the integral also, so that it becomes epsilon 0 partial E partial T. So it is a partial derivative. So with the same argument, we can write it as curl of B equals mu J plus epsilon 0 partial E partial T. So this is how we derive all the Maxwell equation into the differential form. So that's what we done, and we talk about the conservation of charge. Conservation of charge is written like this. The charge density with respect, take the time derivative. Take the time derivative of the charge density plus the gradient of the current density equal to 0. So you can imagine something like within this volume, there may be some current density throwing out this volume. there may be some current density. And if there are some current density flowing out, then the charge within this volume should decrease. Oppositely, if there are some current density going inside this volume, then the charge density should increase with respect to time. This is what the conservation of charge means. The rho is the charge density over space, J is the current density. And how does it come from? It is something like we have I equals the surface integral of J, surface integral of J. And using the divergence theorem, we can convert the surface integral into a triple integral, but we need to add a divergence operator for the current density. And actually, I is the time derivative of the charge, and the charge can be written as the triple integral of the charge density. So that we put the time derivative into the integral, and then we make it a partial derivative with respect to time. Then this one should be equal to this one. So we can write like this. And with the same argument, we can write the conservation of charge like this in the differential form. Any questions? So here shows the relationship between the conservation of charge and the Maxwell equation. This will tell you that in chapter 32 in the textbooks, it tells you that Ampere's find that Ampere's law should have this term, and Maxwell find this term, and then they finally add these two terms together to make it the Amperean Maxwell's law. But you may question whether it needs the third term or fourth term. But actually, here it tells you that with the conservation of charge, this is the exactly two terms we need. We don't need the other terms to make it complete. These two terms is sufficient, and that is sufficient. So we have the Ampere's law like this, and without the divergence, and we take the divergence. We take the divergence of the Ampere's law on both sides. So we have the divergence of the charge density as well as the divergence of E. And we have a theorem like that the divergence of the curl of any vector field is 0. So that the left-hand side should be 0. And we have divergence of J. And this one, according to Gauss' law, we know that the divergence of E should be the charge density over epsilon 0, so that we substitute it into here, and epsilon 0 cancel each other, so that finally we have 0 equals mu 0 times or in parentheses divergence of J plus partial rho partial T. And this is actually the conservation of charge, which means that in order to satisfy the conservation of charge, the Maxwell equation should look like this, but not other terms. Otherwise, if you add the third term, then it will violate the conservation of charge. Any questions? I think we did